The last thing we're going to cover today is an analysis of the learning performance of the three recurrent network architectures that we've looked at, the simple recurrent network, the gated recurrent unit, and the long short-term memory, on what we can think of as a classic stripped down, simplified, but important problem in modeling natural language. And that is learning what we can think of as a counting language. This is a language that is often referred to in the computational linguistics literature. It's described, summarized as A to the n, B to the n, meaning a sequence that starts off with any number of A's from 1 or greater, and must be followed by a matching number of B's, and then must end. And this is probably going to be familiar to you because we looked at a very similar kind of language in the part of the class where we showed that English is not a regular language. That is that regular expressions do not have the, or finite state models, do not have the weak generative capacity to pick out the A to the n, B to the n language. But you may also remember that this kind of pattern was capturable with a context-free grammar. That is, this is a context-free language. In fact, the context-free grammar that you could use to describe this language is actually quite simple and trivial. It's easy to generate. It just has 2 rules. The first one is that the root category, the start symbol S, can rewrite as the sequence AB, or the start symbol can rewrite as A followed by an S followed by B. And if you look at this for a few minutes, it should be pretty easy to demonstrate to yourself that this will generate the language A to the n, B to the n exactly. So let's ask ourselves, well, how learnable is this language for any of the current network models? I claimed to you very briefly that a simple recurrent network model has a hard time learning hierarchy, and this matching number of A's and B's is something you can think of as hierarchy. And let's see how true that is and what the other architectures are like in terms of their performance. So in order to do this, we're going to follow a method that was done by Weiss et al. 2018, 2 years ago, in the Proceedings of ACL, the Association for Computational Linguistics. So they created a training data set. This is a simple stripped down version of their task. Their training set, data set D sub train, was A to the n, B to the n, but it was a bounded number of for n, and they were interested in the question of, so suppose you train on limited data, would the network successfully generalize the pattern? That is, will it generate will it generalize to higher levels of n? So we're going to look at the performance of the 3 different models, the SRN, the GRU, and the LSTM on this. And the first thing I'll do is I'll show you on this training set what the performance is in terms of prediction error. So this is a kind of graph that you'll see a lot in the machine learning literature today. As you saw before, neural networks are trained in epochs. And this is increasing number of training iterations. On the y-axis is a representation of the loss. That is, how inaccurate are the predictions of the model. Of course, the model, what happens at any particular point in the A to the n, B to the n language is not always deterministic. In particular, after a sequence of A's, you may or may not get another A, but that's really the only source of uncertainty. Once you have a B, then it's entirely deterministic what should happen. And as you can see, that all 3 models, of course, learn some kind of patterns. Their loss goes down, but what you can see is that the SRN ultimately performs the worst, the GRU performs less worse, and the LSTM performs the best. So that's the loss, but then you can also ask, well, how is the LSTM performing better than the 2 other models? And it turns out that there's a very revealing kind of analysis you can do. That is to peer inside the hidden and cell state contents. And here is what we see when we look. So what I'm plotting for you here is I'm plotting for you a case where I've set n is equal to 50 here. So that is 50 A's followed by 50 B's. So that is outside of the what's the training space. This is a generalization test because it's outside of the training space of the model. And we're asking, so suppose that you have a much longer test sequence. What does the model do? And what I'm showing you is the hidden or cell state representations as as X, the position in the input string, increases. Okay, and so for the A to the N, B to the N language, you can see that the SRN has extremely erratic behavior. Its hidden state fluctuates quite widely. It has learned one thing, which is it's learned that once you hit a B, I don't want any more A's. But it doesn't tell you. It doesn't seem to have any information about when to stop. And that is sort of reflected in the poorest loss behavior of this model. In the GRU, there's a very different kind of behavior, but it's actually quite hard to interpret. Now notice that, remember that LSTM has both a hidden state representation H and a cell state representation C. The hidden state, like the GRU, is a little bit hard to understand, but it turns out that the cell state representation is actually extremely interpretable. And what the LSTM has done, and I should say that these are all cases where I used a hidden layer of size 10. And for the LSTM, that means that the hidden layer is of size 10 and the cell state is of size 10. But this behavior is not particular to size 10. This will be learned with varying size hidden states and cell states. And what you can see is what the LSTM has learned to do is that there's one particular unit in the cell state. In this particular simulation, it's unit 5, that it's learned to use as a counter. For the most part, the rest of the cell state is not used very much, but as A's accrue, the LSTM is simply incrementing the value of that particular cell unit, C5, and it's learned to increment it in the negative direction, although with different training runs, you'll get it either the positive direction or the negative direction. The direction is not important. What's important is that it's learned to use this cell state unit as a counter. And there's a constant increase in the counter value for every A and a constant decrease in the counter value for every B. So actually the LSTM's superior learning performance in this A to the N, B to the N language is is supported by an actual interpretable, sensible, language reflecting use of the cell state. So I can now summarize what we've done for today. So we looked at applying recurrent neural networks to language. We looked at the very beginning of today at using learned word embeddings for a neural engram model, but we spent the majority of today on recurrent neural networks that use a recurrent state representation to explicitly update a context representation continually with new inputs. We saw 3 different recurrent state representations: the simple recurrent network, which is an undifferentiated hidden state; the gated recurrent unit, which had some clever behavior in when to forget hidden state and when to update it; and the long short-term memory, which explicitly differentiated between a cell state, which was a little bit easier to use as a long-term store of information to propagate information over longer distances, and then the hidden state as well. And what we found is for the classic counting language, which reflect one signature property of natural language, the LSTM performed the best. Thanks, that's the end of today, and we will continue on next time with more investigation of how recurrent neural network models behave for many kinds of language processing behavior. Thanks.